Okay, time for lesson 4, conservation of energy. This is kind of the point. The big idea of everything that we're going to do in the energy unit is this idea that energy is always conserved. So, conservation of energy is a law. So remember, in science, a law means something that is mathematically true. There are no exceptions. In fact, there's even a line in Canadian patent law that expressly forbids you from patenting anything that claims that you get something from nothing, that claims that you get extra energy produced, because literally it mathematically can't happen. It's not possible. It's not just that there's no way we found yet, it's that the universe forbids it mathematically. So here's the law. Unless work is done on or by an object, so unless you've added energy or taken energy away from a system, the total mechanical energy of that system has to remain constant. So what that means is energy can change what it is, but you can't change how much of it. You can't get something for nothing, and you can't actually lose energy unless it's taken away physically from an object. So the total mechanical energy, when we talk about that, it's the sum of all the energies that are on it. So if you just add them up, it's the total energy is the gravitational plus the kinetic plus the elastic plus the electric plus all sorts of other types of energy we're not going to talk about in this class. So what's going to happen is the total energy will stay the same, but energy can be converted between the different forms. So energy can never be created or destroyed. So never. Only transferred into other forms. So when you think something's losing energy, it's not really losing energy. It's typically that's energy being turned into something that's not useful. So for example, if your car's not running right, it'll run hot because it's losing energy to heat. It'll be loud. You'll hear clanking because it's losing energy to sound. So it's not really losing. The energy isn't vanishing. It's staying the same. It's just some of it's being turned into forms you don't want. So, we know energy transformations. You eat food, you turn chemical energy into the physical energy that makes your muscles move. Radiant energy from the sun turns into chemical energy in photosynthesis in plants. Chemical energy makes your car go. Electrical energy can turn into thermal energy in your oven. Okay, so all energy isn't created or destroyed, it's just transferred into other forms. So, mathematically, the easiest one, the one we're going to look at in this class, is going to be the interaction of gravitational and kinetic. So, think of a roller coaster, which is actually why we're going to try to get you to Wonderland. When something is raised, you're doing work to give it gravitational potential energy. When it falls, that potential is converted into kinetic energy. But the total energy is going to stay the same at all points. So the only work we actually do at a roller coaster is when we bring you, when they lift you up to the top of the highest part. After that, you're just coasting. So you start off with a high potential and low kinetic. As you get to the bottom, you have a low potential and a high kinetic. But the total energy will actually still be the same. That's why every successive loop on a roller coaster is a little shorter than the last, so that you basically can keep going throughout the entire thing. Now the trick for this is going to be, you're going to have to calculate gravitational and kinetic energy at two different points in time. So you'll be asked, you say, well, I thought the gravitational was this, or I thought the kinetic was this. You're going to have to sort of switch your head into this idea that you're looking at gravitational at one point in time, looking at gravitational at another point in time, and seeing how it's changed. So, for example, you got a 75 kilogram diver on top of a 10-meter tower. By the way, I really find drawing pictures helps quite a lot when you're trying to solve these, because, as I said, you're dealing with two different points in time. So, you got your diver, and she's standing on top of a 10-meter tower. So, what's her gravitational energy at the top of the tower? Well, gravitational energy, e.g., is just mgh which in this case is 75 times 9.81 times 10 which is 7,000, and we've got two digits, so it's going to be 7,400 joules. By the way, because you do a lot of different calculations in these, make sure you're doing significant digits. Don't put in 7,357.5, because you're going to get a really weird answer by the end of the question, okay? And it'll look very different from mine. So, what's the total energy? Well, her total energy, if she's standing there on top of the tower, she's not moving, she has zero kinetic energy. So her total energy being gravitational plus kinetic, but the kinetic energy is equal to 0. So her total energy is 7,400 joules. Now, that's really important because on her trip down to the water, that's all the energy she gets. Because once she steps off it, there's no work being done on her, she's not going to change. So there's no way for her to get more than 7,400 joules at any point in this question. So as she falls, it's going to be converted from gravitational to kinetic. So, halfway to the water. Well, we're going to draw our little thing. Bring that back. So, halfway to the water, she's now at 5 meters. What's her total energy? Well, her total energy is exactly the same. It never, ever, ever changes. Okay, what's her velocity now? Well, we know she's lost half her gravitational. Where that energy's gone must have turned into kinetic. So, let's do the math here. I need to make this a little bigger so you can actually see what I'm doing with the math. So, let's work through this. Her total energy is gravitational plus kinetic. But now kinetic isn't going to be 0 anymore. So that total energy of 7,400 is now equal to mgh plus the kinetic is 1/2 mv squared. Now, we just plug in numbers. That's 75 times 9.81 times the new height, which is 5 meters, plus 1/2 of 75 times the velocity squared, which is what we want to know. So, by the way, in these, it's much easier to plug in numbers. As long as you're keeping your significant digits, you don't need to worry about what's happening with rounding errors. Just basically keep track. Now, not surprisingly, if you solve that, you're going to figure out that your 7,400 joules, you've lost half the height, so not surprisingly, this is actually 3,700 joules, half of 74, right, because you've lost half your height, plus 75 divided by 2 is 37.5 v squared. So, let's do some quick rearranging. V squared is 7,400 minus 3,700. So total energy minus the gravitational you still have will be the kinetic, which makes a lot of sense. Then we just divide it by 37.5. We divide that across, and we find, and then to get rid of that, we'll take the square root. So we get V equal to 7,400, the total energy, minus the part that's still gravitational, divided by 37.5. And if we then take a square root, we find that her new velocity is 9.9 meters per second squared. Now, why this is cool is, if you know the total energy, there's only two things in this entire equation that can change: the height and the velocity. If you know one, you can figure out the other. If I tell you any change in height between 10 and 0, you can find the velocity. Or if I tell you any velocity, you can figure out what height she's at when she's at that speed. By the way, if the velocity ends up being too big, this will naturally give you square root of a negative number, which will basically mean there's no real solution. She never gets to that velocity before she lands. So, let's go back to our roller. Now, consider a roller coaster with a 50 kilogram object on it, okay? At the top of your roller coaster, you got a 50 kilogram object. So point one, what do we know? Well, your energy is all gravitational. So your total energy, which is just mgh, is 50 times 9.81 times your height, which is 4. So 50 times 9.81 times 4, it's a very small roller coaster, by the way, is 1,962. Now, we'll assume you have 2 digits, okay? So it'll basically be 2,000 joules. So what that does for you, you now know at every point when you're designing a roller coaster that the total energy must be 2,000 joules. It's always going to be the same from the beginning to the end of your roller coaster. The only difference is going to be what is how much of its potential, how much of its kinetic. So at position 1, it's all potential, you got no kinetic. At position 3, you got 0 height, your potential is 0, so you know your kinetic energy has to be 2,000. At position 2, when it's going over, you need to make sure it's going around the loop with the right velocity to actually give you enough centripetal force to keep you stuck to the loop. We'll deal with centripetal force and motion in a circle in grade 12, but the basic idea is you know what velocity you have to get you around a loop of a certain radius. And the way you can design that, how high that loop can be, is you just use the total energy is gravitational plus kinetic. So if my total energy is 2,000, I can find my gravitational from mgh and that'll tell me how much I've got left over as kinetic. So in this case, it's 50 times 9.81 times 3, which is 50 times 9.81 times 3 is 147. Oh, sorry, 14,000. So round it up, we'll say 15,000. So you started off with 2,000. 1,500 is still gravitational. That means your kinetic energy must be 500. So why is this cool? Well, it's cool because at any point on, so for example, let's say I wanted to know right here what that velocity was, how much I needed to brake to stop my roller coaster. Let's say this is where your roller coaster stops at the end. I would simply, if I knew the height, I could figure out how much kinetic energy I have. That's how much work I would need to do to get rid of that energy. So the cool thing is, if you know the total energy, so for conservation energy questions, step 1, find the total energy. And I will always give you the information that you can somehow find what the total energy is going to be, okay? You will always get away at the beginning to find what's the total energy. Then the important thing to remember is that total energy will be the same everywhere. So you know one thing. Then I'll either tell you a height or a velocity, and you can figure out what that object is doing at any point in the future until it ends up having work done on it or work done by it, which will be grade 12 stuff. So you'll have work done at the beginning to give it energy, then its energy will stay the same. And that is the law of conservation of energy.